Buongiorno a tutte e a tutti, benvenuti e benvenute a Biennale Tecnologia, buona domenica. Anzitutto, come sapete, e siamo contentissimi di vedervi così numerosi, l'apertura di questa domenica mattina qui in Aula Magna è dedicata a un ospite d'onore che siamo felicissimi di avere qui con noi a Torino a Biennale Tecnologia, quindi accogliamo, come si deve, la professoressa e Premio Nobel Hanno. Thank you very much, Professor, for being here with us today. Partiamo con un po' di saluti di benvenuto, iniziando ovviamente da chi rappresenta la casa, il padrone di casa, il professore del Politecnico, nonché curatore di Biennale Tecnologia, Juan Carlos de Martin. Benvenuto professore, buongiorno. E grazie.
Grazie mille. Grazie, benvenuti nell'aula magna del Politecnico di Torino. Io sono Juan Carlos de Martin, sono il professore qui e curatore di Biennale Tecnologia e questa grande manifestazione su tecnologia e società. Parliamo di tecnologia, che è una cosa nostra, politecnica, ma la facciamo col contributo di umanisti, di scienziati sociali, di artisti, con mostre, con spettacoli, con lezioni prestigiose, e questa è assolutamente una lezione prestigiosa che siamo felicissimi di ospitare. Quindi grazie alla Conferenza Italiana degli Studenti di Fisica, grazie per questa bellissima collaborazione, grazie a voi per essere così numerosi presenti oggi, una domenica mattina. Siamo molto felici della presenza di giovani non soltanto a questo incontro, ma a tutti gli incontri di Biennale di quest'anno, è una cosa che ci rende particolarmente felici e commossi. E grazie naturalmente alla professoressa Hanno per essere qui a Torino e essere qui al Politecnico. Grazie e buon incontro.
Grazie professore, lei citava appunto la Conferenza Italiana degli Studenti di Fisica che, come sapete, ha coorganizzato questo incontro questa mattina insieme a Biennale Tecnologia, e allora invito a raggiungermi qui sul palco uno studente di Fisica dell'Università di Torino, nonché curatore di CISF 2024, Nicolò Bagnasco.
Grazie Gianluca, thank you very much Professor Lullier for being with us today. Io sono onoratissimo di avere l'onere, anche appunto l'onore, di poter dire due parole all'inizio di questa conferenza, perché le persone con le magliette viola e i badge viola, ma anche quelli che se ne sono dimenticato e hanno deciso che dopo 5 giorni non potevano più metterle, che vedete in questo primo settore, sono 170, quasi 170 fra studentesse e studenti di tantissimi atenei da tutta Italia, accomunati quasi tutti dallo studio della fisica. E questo evento è il gran finale di 5 giorni di evento, la Conferenza Italiana Studenti di Fisica, che è la sua 8ª edizione, che celebrano anche i 10 anni dalla nascita di un'importantissima organizzazione che è l'Associazione Italiana dei Studenti di Fisica. Sono state 5 giornate di esperienza immersiva per i nostri accreditati, alla stregua di conferenze, eventi, visite ai laboratori, che hanno cercato di presentare le realtà della ricerca, della didattica, della fisica sul territorio di Torino. Era dunque di grande interesse per noi questa tematica della fisica dell'atto secondo e accogliere la professoressa che in questa conferenza, che sarà una più che degna chiusura dei nostri 5 giorni di evento. Come sapete, la professoressa Lullier ha vinto, come accennava Gianluca, il Premio Nobel per i suoi grandi contributi nel campo della fisica dell'atto secondo, un campo di grandissima attualità, e quindi siamo molto contenti di poter approfondire questo soggetto con la professoressa. Quindi io vi ringrazio per essere qui, ringrazio i nostri 170 accreditati per essere ancora al 5° giorno alle 10 di mattina a seguire conferenze di fisica, e ringrazio il pubblico per averci accolto così calorosamente in questa sala. E ne approfitto per invitare sul palco una rappresentante della città di Torino che ha dato un grande supporto nello sviluppo e nella progettazione della nostra conferenza, l'assessora Carlotta Salerno per l'istruzione, le politiche giovanili, le periferie e la rigenerazione urbana della città di Torino. Grazie e buona conferenza.
Buongiorno a tutte e tutti, io ho sempre qualche problema con i leggi, sono un po' piccola. Sono felicissima ed onorata di essere qui per un brevissimo saluto per lasciare poi posto all'argomento importante della giornata e alla relazione della professoressa Lhuillier, che sono onoratissima di aver incontrato e conosciuto in questa sede e che credo sia meraviglioso possa essere qua in questa mattinata. Ho avuto l'onore di essere presente alla conferenza stampa di lancio di Biennale Tecnologia. Adesso che Biennale Tecnologia si sta concludendo, credo che il cerchio si chiuda e che siano stati giorni assolutamente meravigliosi. La vostra presenza qui oggi è ancora l'ennesima testimonianza, da un lato dell'energia che abbiamo nelle giovani, nei giovani, nella voglia di essere presenti quando gli argomenti valgono la pena, nella voglia di mettersi in discussione, riflettere e ragionare, anche di mattina alle 10 di domenica senza esitazioni. L'impegno del gruppo che ha organizzato la conferenza italiana degli studenti di fisica, che voglio ringraziare e che è stato un gruppo stupendo con cui abbiamo lavorato e abbiamo patrocinato con grande piacere l'evento, e tutti coloro che hanno collaborato a Biennale Tecnologia. È un grandissimo orgoglio per la città ospitare ed essere il palcoscenico di Biennale Tecnologia, come lo è nell'anno alterno di ospitare Biennale Democrazia. Sono ossigeno puro, energia che si propaga per la città, possibilità di mettere in moto le nostre menti e i nostri cuori e la possibilità di non fermarci, di non atrofizzarci e di non invecchiare nella testa più che nel fisico e nel corpo. Quindi essere qui per me è davvero un grande onore, darvi il benvenuto è un grande onore, sono sicura che sarà una lezione meravigliosa, ma tutto il percorso che voi state facendo. Quindi spero che continuiate così ad impegnarvi con passione, con grande approfondimento scientifico e con grande generosità per la scienza, per l'impegno civico, per la città, per l'Italia e per tutto il mondo. Grazie davvero e buon lavoro.
Grazie Assessora Salerno per la sua presenza qui stamattina, grazie a Nicolò Bagnasco, e ora siamo arrivati al momento della Nobel Lecture, quindi passiamo dall'italiano all'inglese, we switch to English. Vi ricordo che per chi sta ascoltando tramite le cuffie il canale dell'italiano è il numero 1, il canale dell'inglese è il numero 2. And so it's time to invite here on the stage Professor Lhuillier. Good morning, Professor Lhuillier. Thank you for being here. Professor Lhuillier has won many different prizes in her career. The Nobel Prize in Physics in 2023. Today is a professor at Lund University in Sweden. And so the stage is yours. And thank you once again for being here.
Thank you very much. You can hear me? Yes? It's a real pleasure to be here in Torino, first time. So I will tell you about attosecond pulses, and this is a little bit a historical talk. I'm going to tell you about this field of physics, how it started, the main progress, the main steps, and I would like to acknowledge my two co-laureates for this Nobel Prize, Pierre Agostini and Ferenc Krausz. So I will start with a little background. This field of research would not exist without the invention of the laser in 1960 by Theodor Meinmann. Here you have one of the first laser ruby laser. Nobel Prize for laser went to the background for the laser to Towns, Basov, and Prokhorov in 1964. And in our research, we used two properties of lasers. The fact that we can confine the light in short pulses down to femtosecond, and also the fact that it's intense radiation. So the invention of the laser opened many research fields. One of them is called nonlinear optics, and this is the field where you generate new frequencies by absorbing laser photons. So here you absorb 2 laser photons and you emit a photon at frequency 2 omega. This is second harmonic generation. And here you have a picture of the first setup that was used by Peter Franken in 1961. And we're going to use very similar setup. We have a laser, in this case the first laser, ruby laser, a focusing element, a lens. Then the light is focused into a material, here a crystal of quartz. And then you have an element to analyze the radiation, in this case a prism. And then you have a detector. Nobel Prize for nonlinear optics went to, the father of nonlinear optics is Nicolas Bloembergen, and the prize was for the development of laser spectroscopy to Bloembergen and Shallow in 1981. It's interesting to also mention the third Nobel laureate that year, to Kai Sidbang. It's a Swedish physicist, and this was for the high-resolution electron spectroscopy. And I'm mentioning that because in what I'm going to tell you, we are using a lot electron spectroscopy. The other field of research that started after the invention of the laser is atoms in strong laser field, multiphoton processes that were predicted already in 1931 by Maria Göppert-Mayer. So here you have a picture of a 2-photon excitation process where an atom can absorb 2 photons and be excited. You can also have a multi-photon ionization process, as here on this picture. Here an atom absorbs 4 photons and then is ionized. Pierre Agostini in 1979 discovered the process of above-threshold ionization, where an atom is ionized by absorbing more photons than what is needed for ionization. And you can detect these processes by looking at the energies of the electrons that are being emitted. And then the beginning of the 80s, this is when I was a PhD student, and my thesis was about multiple ionization of atoms using multiphoton absorption. For example, here we could produce xenon plus, but also xenon 2+. So at this point, we thought, oh, okay, in this interaction between atoms and laser light, we probably produce excited atoms or excited ions. Let us look at the light that would be emitted when these excited atoms or ions decay. So we set up an experiment. So now we are at the end of the 80s. I had become researcher at the Commissariat Énergie Atomique in close to Paris in France. And we set up an experiment where we want to look at the fluorescence light emitted by atoms exposed to an intense laser field. And you have the principle of the experiment here, an intense laser pulse is focused into a gas of atom, and we look at the radiation. The radiation can be emitted in any direction. Fluorescence is emitted in any direction. So we look along the propagation axis here and also perpendicular to the propagation axis, using not a prism, like in the Peter Franken experiment, but a grating to disperse the radiation in different directions, and then a detector. And the laser looked like this. It was a neodymium YAG laser, picosecond. The wavelength is 1 micrometer. And here you can see this, when you see this picture, you realize that it's really old technology, and things have really become better. But you can see here the oscillator with the 2 mirrors. This is the crystal where the laser is born, and then you have 2 amplifiers. And this is a picture of the setup. So the laser is coming from the right. There is a gas jet somewhere here. This is the lens. This is a vacuum chamber. And then we have these 2 detection axes along the propagation axis, and then perpendicular to it. You can notice that there is a printer here. This was before personal computers existed. It was end of the 80s. So in this case, we were using a printer, and the pen of the printer was coupled to our detector. And the experiment consists in rotating the grating and then looking at the radiation in one direction. And so we were, this pen was really moving like this, and then comes a peak, and so it was how we were taking data at that time. So we never saw anything perpendicular to the detection axis, so I'm not going to discuss that. So we saw instead radiation that were really very well directed along the laser propagation axis. And we almost didn't see fluorescence light. Instead, what we saw is high-order harmonics of the laser field. So this is one of the first spectra. So what you see here, the peaks, the numbers here refer to the order of the harmonics, which means that, for example, 17 means that we see a harmonic with light with frequency equal to 17 times the laser frequency. So it's a multiple of the laser frequency. And what was very unexpected is first the presence of many harmonics, up to 31, even 33 here. And the really surprising result was this behavior of this is the intensity of the different harmonics plotted in a log scale, so as a function of order. And you see that there is a plateau, which is then ending up with a cutoff. But the really unexpected result is this plateau. And the reason is that we were thinking very much in terms of perturbation theory, where a medium which is exposed to a laser field, represented by E here, the electric field of the laser. So we were thinking in terms of an expansion, Taylor expansion, if you want, in powers of the electric field. And for this expansion to be valid, you expect the first order to be much larger than the third, much larger than the fifth, etc. And obviously, this was not the case. This plateau means that we are in a non-perturbative, highly nonlinear, but also non-perturbative regime. This was really the unexpected result. You can notice that we only have odd orders, and this is because of a symmetry of the process. The gas is centrosymmetric, and because of this symmetry, we don't produce even harmonics. So how can we understand? Yeah, first of all, I want to say first that if we start from infrared radiation, this is where the frequency of the laser, and you multiply by, let's say, 33, you end up into the extreme ultraviolet region of the spectrum. So it's above ultraviolet and it's below X-rays. And this radiation is invisible to us, and it's also absorbed by air and by matter in general, which means we need to work in vacuum. This is why we have these vacuum chambers in our experiment. The second thing I want to say is to make an analogy here with harmonics in music. I'm sure you have heard, maybe not about this high-order harmonics of light, but harmonics in music. All music instruments produce not only a certain tone, but overtone harmonics. This is, for example, a spectrum produced by an alto violin. So if you excite the string corresponding to this A note, you get not only this, but also many harmonics, and this is what is producing the clang of a music instrument. Now, in here, we have atoms exposed to a laser pulse producing many harmonics. So in both cases, we have a strong interaction here between atoms and a laser, and here it's between the string of a violin and the bow, leading to these harmonics. But of course, these are harmonics of sound, and here it's harmonics of light. So this field is in between two fields. One is atomic physics, quantum mechanics, microscopic, and the other one is nonlinear optics, which is a response of a medium to radiation. So to describe high-order harmonic generation in gases, first you need to describe the single atom response, which is described by the Schrödinger equation, as you can see here, where the interaction is due, of course, to the atomic potential and to the laser atom interaction, as written here in the dipole approximation. So here it's good enough if we describe the laser classically, so this is not quantum optics, it's classical optics, and then in the dipole approximation. The difficulty is that these two quantities are comparable. So this is where this is a strong interaction, and it's beyond perturbation theory. But we also, now this has stopped working, or is it working? No. It's working? Yeah? Okay. So the second aspect is the many atom response. We have a medium, many atoms, actually trillions of atoms in this medium. And this problem is described by Maxwell's equation of electromagnetism, which can be simplified to a wave equation. So this is the propagation of a field, the generated field, with a source term in this wave equation, which is the polarization of the medium. And in order to have efficient harmonic generation, it's important that a certain phase matching condition is realized, which means that the emission from all of these atoms should be at the same time phase matched. And you can also make a small music analogy here. This medium is really very sensitive thing. This medium is behaving like a gigantic orchestra with many, many musicians, trillions of musicians, and these musicians need to play music to produce these harmonics at the same time. So the first attempt to understand this phenomena was to exactly to solve these two equations, Schrödinger equation and then the wave equation. And here is the result obtained already in 1989. And here you compare the response of a single atom with experiment. And you see that the agreement is actually quite good. These are the experiment and these are the theory. And in itself, it was a surprise because we thought that phase matching would be more and more difficult to achieve for these very high order harmonics. And according to this result, it was really the single atom response producing this characteristic behavior with the plateau and the cutoff. So it was important to also solve this Maxwell equation, wave equation, and here you have some results at different laser intensity, reproducing more or less the experimental behavior with this plateau. Okay, so now we can simulate our result. Does it mean that we understand the physics? Not really. So this is also the time, so we are at the beginning of the 90s, where the idea of attosecond pulses was proposed. And let me explain the idea very simply. So let's consider three harmonics, for example, 17, 19, 21. And so these are waves at slightly different frequencies. Let's assume that these three harmonics are in phase. The maxima here coincide at a certain time. Okay, because of the periodicity of this process, half a laser later, then the minima will coincide. And then half another laser cycle after, the maxima will coincide, and then the minima and the maxima. So we assume this. This is also called phase locking. We assume that harmonics are phase locked. Now, if we now sum these three harmonics, we have constructive interferences at this time, and again, and again, and again, and destructive interferences in the middle, where you can have both minima and maxima. So we can confine light into very short time intervals and produce this train of attosecond pulse. We can plot, this is the electric field. We can also plot the intensity, and we obtain something like this, corresponding to very short pulses. We are in the range of 100 attosecond, 10 to minus 16 seconds, so the very, very short light pulses. If we have not only 3 harmonics, but 10 harmonics, then we can produce even shorter pulse. This is just an expression of Heisenberg principle. If you have a broad bandwidth and this fast-locking condition, so broad bandwidth, then you can have extremely short pulse in the time domain. You're well decided in time, not decided in frequency, well decided in time. This is Heisenberg principle. So the question was, is this true? Are these harmonics in phase? So very exciting. And this was exciting for the following reason. Parallel to this, there has been progress in laser technology, and in particular progress in making laser pulses shorter and shorter, but there was a kind of a stop around a few femtoseconds. So this is the evolution of the pulses from dye lasers in the 70s, 80s, with some kind of stop around 2 or 3 femtoseconds. And a little bit later, the titanium sapphire laser will also lead to very short pulses, but again, some kind of stop around 2-3 femtoseconds. This was even called the femtosecond barrier. And the reason for this is actually we want to talk about light. So we would like to have at least one oscillation in the wave, in the pulse. And one is limited by the duration of an optical cycle, which depends on the frequency. So in order to get short optical cycles, which you need if you want to get short pulses, you need to have high frequency. The second condition to produce short pulses, as I just explained, we need broad frequency. And this was the hope with these high-order harmonics, because we were both high frequency, we are in the extreme ultraviolet, so very short optical cycles, and a broad bandwidth, this harmonic comb that I showed you before. But the question was, are the harmonics phase-locked? So now we are in part 2, progress in technology and in understanding. So I'm going to start by progress in technology. Technology is very important and has pushed this, our field of research very, very much, and is still doing that. At the beginning of the 90s, there was a huge progress in laser technology with 3 discoveries that arrived at the same time. The first one is the so-called chirp pulse amplification, which is a technique to amplify light pulses, and that led to a Nobel Prize to Gérard Mourou and Donna Strickland in 2018. There is the discovery of a new laser medium called titanium sapphire by Peter Moulton in '86. And then a new method to produce very short pulses from laser oscillators called Kerlens mode locking. And here you have 3 Swedish scientists that look at these 3 discoveries, and they wanted to start a new research program in Lund. This is south of Sweden. And they decided to put together these 3 technology and to actually to buy a prototype, and they bought the first terawatt laser based on titanium sapphire at the Lund Laser Center, and this laser was going to be a unique laser in Europe for many years. Then titanium sapphire technology was going to be the main, the base for the research that we do on attosecond pulse during 20 years. So very important progress in laser technology. In parallel, I was still young researcher in France. You have, this is a picture of me a long time ago. And this is my first 2 PhD students back in close to Paris. So we built dedicated instrumentation to study the process of high-order harmonic generation, which looks like this. There is a gas jet here. Then you have optics, which are in this vacuum chamber. And then you have an electron detector, which is here. This is also the time where personal computers arrived in the laboratory. And they looked something like this, not at all like today's, but this was a really important step. We start writing data acquisition programs that allowed us to now to take data live and be able to really check, oh, is this correct? Do we have too much noise? So this was a huge step in how to do experiments. So the Swedish scientists called us and asked us if we would like to perform joint collaboration, look at high order harmonics with their brand new laser system, which was a really fantastic laser for this type of studies. And of course, we say yes. This was also the beginning of European collaborations and supported by the EU instruments, so it was really interesting. So we moved this equipment to Lund. We did experiment, and the reason why I'm in Lund now is because I met my future husband, so I moved back later on to be in Sweden. So this is some example of results that we obtain. You see that now we generate harmonics in helium, and we really get very, very many harmonics up to the 93rd harmonic. And you see that we reach wavelengths down to 8 nanometer. And thanks to both the laser repetition rate was 10 hertz at that time, and this new way to do experiments with computers, we could now not only take a spectrum, as you see here, but also study how the processes vary as a function of different parameters. For example, here, the laser intensity. This is also the time where there is a huge progress in understanding, and this was thanks to the theorist. The Nobel Prize is awarded to experimentalists, but I think theorists have also played a very, very big role in this field of research, and in particular, this very intuitive understanding of the process. So this is called the 3-step model from Ken Kullander, Ken Schäfer, that you see here, also Paul Corkum at the same time, and Levenstein, that you see here, also produce a quantum formulation of this model called strong field approximation, and which was going to be very, very important in our field. So I'm going to describe this, and then I will propose to you, especially I heard that there are some high school people here, I will produce a kind of analogy, an illustration if you want, okay? So first, a little bit of atomic physics and quantum mechanics. So what you see here is an atomic potential. It looks like this normally, Coulomb potential. You have an electron which is bound to the nucleus, and this electron is in this strong potential. Now, because of the interaction with the laser field, this potential is bent in one direction. So this potential has the revolution symmetry, but then the laser is kind of bending the potential in one direction. So here you have a potential barrier, and this is quantum mechanics, so the electron here has a certain probability to go through this barrier, and then the electron is driven in a laser field. Then the electron is driven back when the laser field changes sign. And then there is a certain probability for the electron to recombine back to the ground state. And in this process, so the electron has gotten a lot of kinetic energy, so the extra energy is liberated as a photon in the extreme ultraviolet range. So this is a light pulse. So I promised a small analogy. So this is called, this is even in Swedish. This means, then, I think you can understand, the adventure of an electron in a laser field. So, so here is an electron. Yes. And you can represent this like this. Yes. This is an electron in a prism. And on the side there is, now I have to explain what this is because my drawing are really too bad. But this is a roller coaster, yes? In French this is called montagne russe. I don't know how it's called in Italian, but So the electron would like to have fun. So what does the electron do? Come on now. You have to speak louder because I don't what does the electron do? Escape. How? How does he escape? Or she? I don't know if it's a he or she. What did you say? No, it does not go up. It does not break the bond. What does he do? Remember the previous slide. Yes, I think I saw at least some people. So this is really. It makes a tunnel. You agree? Yes. And then everything is fine. This is too sensitive. Yes. The electron is happy, and he's going up and down. It's now this is a gravitation field. In reality, it's the electromagnetic field, but it's very similar. Gains energy and lose energy. This story is finishing very bad. Sorry. So the electron is this roller coaster is just happened to be just above the prison, which is open, of course, and the electron is just falling. And when he falls, well, he has a lot of energy. This energy is a scream in this story. In reality, it's a light pulse. This is end of the story. Yes. Yes, thank you. And you got a little bit of Swedish on the side, but this is not too difficult. Okay, so I go back to the attosecond idea. So now we understand much better what is going on. We have an intuitive picture of the process. And this is just a recap of the idea. Well, if there is phase locking of all of the harmonics, then we expect one light pulse per half cycle. So now we can calculate the temporal emission in this adventure, or in this process. And what do we get? Well, we don't get what we would like to happen. It's actually a temporal emission all the time. And it's a little bit of a mess, and you have especially 2 peaks per half cycle. So this is what happens sometimes. You understand things better and better. You have an idea, and this idea crashes. So the reason for these multiple peaks, you can actually understand by looking at the possible trajectories that the electron can take in the continuum. And when you look at that, you realize very easily, this is just solving Newton's equation. I usually propose this for my master students to look at. So you realize that you have a short trajectory where the electron is tunneling at some time and then coming back almost immediately. And you have long trajectories where the electron is tunneling actually a little bit before, takes a long time. The excursion is like a few nanometers, and then come back with approximately the same trajectory. So you have several trajectories leading to the same final energy And this is represented by the colors. And this explains these multiple peak structures. And looking at the phase difference between the consecutive harmonics, you find that, well, it doesn't work. It seems that the phases are random. They are not random here, but this is the cutoff region, which is not so interesting because there are no photons. So conclusion is that the harmonics are not phase-locked. Okay, so it was a little bit disappointment, but of course we continue to study these processes. And this is an experiment which we perform now. We are at the end of the 90s together with Ted Hensch. Mette Gård was my first PhD student in Sweden, Marco Bellini. And the idea of this experiment was to look at the coherence of the high harmonics. Is it coherent light? And to do that, we make a replica of the harmonic sources. And we look in the far field, and we see whether the light emitted by these two sources, if they interfere. And this is the result. On harmonic 15, you see indeed the interference fringes, which is very nice. This light is coherent. But you also see these two regions, collimated radiation here. This is a picture of the beam. So we make an image of perpendicular to the propagation axis. You see that there is collimated radiation and much more divergent radiation. And this is the first time that these two trajectories, which I mentioned, were really observed in the laboratory, with a short trajectory leading to collimated radiation, and then this long trajectory leading to much more divergent radiation. And the reason is that along this trajectory, the electron is picking up a phase, and which depends on the laser intensity, and this leads to different wavefronts, and much stronger wavefront for the long trajectory leading to divergent light. We can also vary the delay between the two sources, and you see that the fringes have disappeared for the long trajectory, but they are still present for the short trajectory. So here we see that these two trajectories have different physical properties. And if we can see measure these different properties, that also means that maybe we can control them. And obviously, there is one thing that we can do here is we can simply aperture the beam in the far field and this way select only one trajectory. We also make progress in the second aspect of the problem, which is the nonlinear optics part. And very briefly, what we realize is that in order to realize phase matching, we need the phase velocity of the field which is generated to be equal to the field that drives the process, the fundamental fields. In other words, these two wave vector here should be equal so that these two fields propagate together. And so we can express it like this. This is very similar to harmonic generation in crystals. In our case, this phase mismatch depends on three different quantities: dispersion in the partially ionized medium, focusing of the laser, and the electron trajectory. So you also see here that possibly these different electron trajectories might not be phase matched in the same condition. So this is a natural selection of one of the trajectory. So, and indeed, these are simulations showing that, so this is the single atom response, and in blue, it's the complete calculation. In some conditions, we can get back this simple picture of one pulse per half cycle, which means that we have phase-locked synchronized harmonics. So we are now at the end of the 90s. We understand much better the process. We think that in some conditions, this can lead to attosecond light pulse, very short pulses. At the same time, we would like to show it in the laboratory. We would like to measure the duration of attosecond pulses, and how to do that was not very, very clear. Myself, I was working with a method that never worked. So this was very important to really measure attosecond pulses. And this is what my two co-laureates did, Pierre Agostini and Ferenc Krausz. And they achieved this in 2001, almost at the same time. Pierre Agostini measured the duration of attosecond pulses in a train of pulse, while Ferenc Krausz managed to produce and measure single isolated attosecond pulse. So I'm not going to describe very much what they did. I would like to explain the method used by Pierre Agostini. So this is what I'm going to do now. So the idea is from a theoretical article published a couple of years before, and it uses two-photon ionization. So I'm going back to almost one of my first slides. So now here we have two-photon ionization by absorbing a harmonic photon and a laser photon. So producing a main electron peak here in blue and a sideband peak. Now this sideband peak can be achieved, can be also reached by absorbing the next harmonic in blue and then emitting a laser photon. So this is stimulated emission. So here you have, you can reach this final state by two paths, okay, two quantum paths. So it's a quantum interferometer. We are in quantum mechanics. We need to add the amplitude for this process and the amplitude for this process. And how you add these two amplitudes is going to depend on the relative phases of the two amplitudes. These are complex amplitudes. This technique has been called by the group of Pierre Agostini RABBIT, which means reconstruction of attosecond beating by interference of two-photon transition. So let's look at the phase for these two paths. So first of all, you have the phase of the harmonic, and remember, this is what I want to measure. And you have also a contribution from the atomic process, the two-photon ionization. I'm going to discuss that a little bit later, but for the moment, this phase contribution is actually very small, so let's forget it. Now, on the other path, you have the phase of the next harmonic. Remember, it's only odd harmonics, so they are separated by two. Then you have the laser. So the laser is delayed relative to the harmonics by a delay tau. So you have a phase which is omega tau for this one and minus omega tau for the emission process. So that the signal that you get is an interference signal. It depends on the, there is a cosine, and then here, this is the phase difference between the two paths, phi q plus omega tau, and then minus phi q plus 2 minus omega tau. So you have this interference equation here. So you see now that by studying this as a function of delay, then you can get information on the phase difference between consecutive harmonics, which is exactly what I'm looking for. And here is the result of obtained by Pierre Agostini. So this is the phase difference between consecutive harmonics. is not like this. So they are not perfectly synchronized. There is a certain chirp, phase difference, but it's not random. So there is a certain phase locking. So now if you use the information that you have on phase and intensity and do a Fourier transform, you get a train of attosecond pulse. So this was this very important result in 2001. Now I would like to finish this talk by talking a little bit about the application of attosecond pulses, how this field is now open to many areas. And I would like to show you two very different applications, one which is extremely fundamental and one which is much more applied. So the fundamental application is really to try to measure the dynamics of electrons using attosecond light pulse, a little bit like using flash of a camera to follow a rapid motion. Here we have our attosecond light pulse, and what we try to follow in time to measure is the dynamics of electrons. So let's consider the simplest process, which is photoionization, represented here. So you come with X-rays or X-UV radiation in our case, and you emit an electron. This is the photoelectric effect explained by Einstein in 1905. I'm sure you think of this photoelectron as a particle, right? It's a particle, and you have a detector. You can measure its energy or maybe momentum. But what we try to do with our technique is really to measure the wave or even quantum property of the photoelectron, or maybe formulated a bit differently, how long time it takes for an electron to propagate in the potential. This process, photoionization, has been considered as instantaneous previously. Now, thanks to our technique, we can really measure the time it takes for this photoionization. So let's take an example, which is photoionization of xenon in the 4D shell. And this is an old measurement performed using spectral lamps back in 1964, and showing here this beautiful result. So this is a huge resonance. It has been even named the giant dipole resonance for 4D to epsilon f photoionization process. And so what is plotted here is the cross-section. So this is the intensity of the probability for ionization, if you want, as a function of photon energy, and you see that we are in the 100 eV range. Now we would like to study this in the time domain. What is the dynamics of photoionization? So this is this process. You ionize an electron from the 4D shell. How long time does it take? So we would like to go from frequency to time. You can do that by a well-known mathematical transformation called Fourier transform. What is missing to do a Fourier transform? The phase information. And this is really what is new, and what we can do with our technique is we can measure phases of photoionization, phase or phase derivative. We don't care about an absolute phase. We just want to measure the relative phase. How do we measure this phase? Going back to this beautiful rabbit technique. And now I'm going to focus on what I have ignored before, which is this phase here, which is related to this ionization mechanism. And just to be simple, let's forget the phase of the harmonics. In reality, you cannot do that, but we can measure it, we can calibrate it, so we know how to deal with it. So let us ignore it. Then our interference signal is now going to depend on this phase, this relative phase for ionization using harmonic Q or using harmonic Q plus 2. So you see that now we have information about this ionization phases. And this allows us to, we call this time delays, to really determine this phase or phase derivative, group delay of due to ionization as a function of photo energy across this giant dipole resonance that I showed you. And these are the experimental measurements. And in black you have theoretical calculation. And we can even identify 2 different regions with the giant dipole resonance, which is peaking at 100 eV, so it's something like this. So this is the delay for the electron to get ionized in this spectral region. And here we have a much larger delay, which is due to the spin-orbit interaction, probably spin flip in this process. Finally, I want to mention another application of the physics I have described to you. And I like very much this application because it's really happening now. People ask me all the time, oh, why is it good for? Well, at least this is one application which is in development at the moment by this company in Holland called ASML, which is building instruments for the semiconductor industry. And the idea here is to use this source to do imaging of silicon wafers on which you have a lot of structures. And this is for the next generation wafers with structures which are of the order of 10 nanometer. And also, these structures are not only in 2 dimensions, but even in 3 dimensions. One that try to pile up lots of transistors, not only in 2D, but also in 3D. And the idea is to use the broad frequency range of these high-order harmonics, which are in the right spectral range, which is this extreme ultraviolet around 10 nanometer, to check, to control that there are no defects on these wafers. So this is happening at the moment, and I'm actually very excited about this application. So with that, I would like to conclude. First of all, I would like to say that at the moment, this field is going into many, many directions, many applications, especially in, I showed you some application where we look at photoionization, but the idea is to look, of course, at much more complex systems and complex processes in chemistry or in condensed matter. We have also this industrial application that I mentioned, and also a certain direction in quantum physics. Attosecond sources have been produced by high-order harmonic generation in gases, but at the moment there is really a new source of attosecond pulses using free electron laser. It's the last 2 or 3 years it has began to happen, and these are much more energetic pulses, but in a different spectral range. So if you happen, like as I have been, to be a little bit, to be lucky, to be at the right time and at the right place, a long time ago, 37 years ago, you might end up here in this room. So this is the Nobel Prize ceremony on the 10th of December, which is the anniversary of Nobel Depth. Actually, not so far from here, San Remo. I don't know how long it is from Torino, but it's not too far. Anyway, and you have Alfred Nobel here. And this is the royal family of Sweden, with the king here. And then you have members of academies. These are the Nobel Prize laureates last year. And yes, and maybe be a happy Nobel laureate. And a few hours later, there is a huge banquet in the Stockholm City Hall. You have 1,300 guests. It's a huge, huge thing. And for a French person like me, you know, educated with the French Revolution, the French Republic, and etc., it's a really experience to be sitting during 4 hours close to the King of Sweden. This is him. And this is my last slide. Of course, this research cannot be done alone, so I've been working with many, many people during my life. This is the present research group. Normally, they are not dressed up like that, I can reassure you. Here they are actually, this is on the 10th of December, they are celebrating together this Nobel Prize Award. This is the name of the senior people working with me, and this is some funders for this research. Thank you for attention.
Thank you very much, Professor Lullier, for being here in Turin today. So we are supposed to have a conversation now on that chair, but maybe we can grab them. Okay.
So
please.
Shall I stop this, or I don't know? Yeah.
Okay. So this would be a Q&A session. We can start from a few questions from me, but then we have time to have some questions from the students too. So be prepared if you want to ask something to Professor Lullier. And I think we can start from the very moment in which you knew that you were winning the Nobel Prize in 2023. If I know it well, you were informed an hour before the rest of the world. How was it?
Yes, this was very special because I was teaching a class. So it's 2 hours from 10 to 12. 100 students from engineering physics in Lund, third year student. I was teaching about fine structure of the hydrogen atom. But anyway, during the pause, I realized that many people have tried to reach me. But then someone is calling me, so I pick up the phone. And this was the announce for Nobel Prize, and they asked me to stay on the phone, and I say it's impossible. I had 100 students waiting for me. So I was able to go back to my class. I tell the students, and it's supposed to be secret 1 more hour until the press conference, which is at 12. So I told the student, okay, I have to leave a little bit earlier, and I think they start guessing at this point. But I continued my lecture, yeah. So I didn't have time to really think or realize anything. The only thing I was thinking was, how am I going to finish this class? So, yeah.
It's really interesting, and you are very keen on teaching to the students. Do you still have lessons in your university?
Yes, I do, actually. Especially in the fall, I'm teaching this big course in atomic physics. I like teaching, so I will continue teaching, yes.
As you were mentioning, you started researching on your main topic of research when you were a PhD student.
Yeah.
So now here we have a lot of students, mainly in physics, I guess. And what would you like to tell to young students in terms of mindset, in terms of preparation, in terms of being curious?
I think in terms of mindset, I would like to say, first of all, you should choose a topic that interests you, that you find is interesting, which was my case for atomic physics and this optics and atomic physics interaction. I was inspired by a very good teacher. Actually, they became Nobel Prize winners afterwards. Claude Cohen-Tannoudji, probably you have read some quantum mechanics book from him, and Serge Haroche. They were extremely inspiring teachers. So atomic physics was what I wanted to do. Then it's always part of luck, and so I had the possibility to become PhD student in this research institute, and I thought this was interesting. Then a little bit going back to the mindset, I think to be a good researcher, you need to be very obstinate. First, you need to like what you're doing, so you need to be passionate, and then you need to be obstinate, and you need to be able to continue even though sometimes nothing is working, or you don't know where it's going, so one needs to be obstinate. Yeah.
You were the 5th woman in history to receive a Nobel Prize in Physics. Yeah. What does it mean for you, and how do you see things changing in terms of gender balance?
Yeah, it means I'm very proud of this, of course, and what I think, what I would like to say is that I think things are changing. You have only 2 women in 120 years, Marie Curie and Maria Goeppert-Mayer. And then the last 5 years, you have 3 women. So there is really a change in tendency. And another reflection which I'm making is that when I began my career, I worked a lot with only men. This is not true anymore. The research group that you saw on my last slide, you have about 37% women. So it is also changing at this level. I have worked with research group with only men and me, and now it's 30-40% women. So I think also I see a change. So I hope this will continue. It will take time, but I think it will be better and better. That's my optimistic view on this.
In the last few months, of course, your life has changed. Yeah. You are still teaching, but you are also traveling all around Europe and the rest of the world to have conferences and to do communication. Which are the main topics and themes you are communicated worldwide now that you are a symbol of research?
This is a very good question. So this is I'm coming to Torino, for example. But I think I am trying to communicate a little bit of enthusiasm for physics. Also enthusiasm for trying an academic career, which is tough, but it's very rewarding. It's very interesting. You learn all the time. And also, I would like to tell, especially the young women here, to yes, you can do research if you want, and it's you can combine family life with research and teaching, if you are a little bit organized and if you want to. So that's what I'm trying to say.
I guess you are receiving really many invitations from all over the world and different countries. How do you choose where to go and where not to go? Because you have chosen to be here in Turin, so.
Yeah. Well, this is very difficult, and probably I'm making wrong decisions sometimes. I try to prioritize the young people and the students and high school. This I'm trying to prioritize. And of course the scientific community. Yeah.
Thank you. And one thing I would like to ask you, but you said it before, so what is all of this, your research, good for? You have already answered it, but what's the relation between basic and applied research? Because when you talk about communication, when you talk about funding of research, there's always this problem of explaining to the general public and to the administrators that basic research we are doing now will be useful maybe in 20, 30, 40 years.
Yes, I think basic research is very important. And it's not, you cannot, it needs to get funded. The application I mentioned, it really came about like 5-6 years ago. And there was never a question to generate high harmonics for this application. It really comes because of the basic, the fundamental research. Now, I would like to say one more thing about, so I explained how we try to measure electron motion in simple system, but I think the real application of our field will happen when we can do that in more complex system, in more complex processes like photosynthesis, chemical or biological processes, because if we have this control and can do this measurement, so these processes are very often, they start by an electronic transition. So at the beginning you have this electron motion. So if we can really watch this electron moving or measure this phase and amplitude as I explained, then that also means that we can control these processes. So I think this will have a lot of application. So that is a little bit, I think, the dream of our field of research. I say dream because it's still very much fundamental research. We are not yet in the industry. Yeah. So maybe one more comment on this is that fundamental research takes a lot of time. You saw this field of research. It started in '87, so it's almost 40 years. And now you see some first applications. So it takes a lot of time, and this time is needed. So it's important that the people giving money to research have this in mind. Yeah.
For a few years, going back to the Nobel Prize, you were part of the Nobel Committee. So yeah, you were looking at Nobel Prizes from the other point of view. Yeah. Can you tell us something about what's going on behind the scenes, how it goes when they have to choose who is the next Nobel Prize winner?
I cannot tell you very much because it's confidential, but what I can say is that it's a very, I would like to say two things. First, it's a very professional process. which has been established during more than 100 years, where every year one looks at nominations and asks for expertise and write a book every year about the work that is done. So it's a very professional process. Now, the second thing I want to say is that the last 5 years, even more than that, 7, I stepped back in 2015, and after that I was not allowed to be part of any discussion or anything, so I was completely out of the process, just for to be clear.
Yes, of course. So, thank you very much, first of all. Is there any question from the public? You may raise your hand. Yes, just in the first row. I don't know if there's a mic coming. Yes? Thank you.
Io chiedo scusa che parlerò in italiano perché il mio inglese è pessimo.
I'll try to translate, yeah.
Nei suoi viaggi intorno al mondo per parlare di questa sua esperienza innovativa della fotonica, la politica che sensibilità ha avuto? Perché qua a Torino non ce l'abbiamo, la politica è quella che gestisce i fondi della ricerca e quindi se non c'è questa sensibilità è difficile avere questi fondi. Seconda domanda, anche perché nell'applicazione una delle forme di applicazione della fotonica che io immagino è quella delle energie rinnovabili, fotovoltaico, è corretto oppure no? Secondo, nella produzione, si può arrivare con la tecnologia fotovoltaica a produzione di scocche di automobili? Grazie.
Grazie mille. So I'll try to explain it in English briefly. The first question is, when you're traveling all over the world, now that you are a Nobel Prize winner, what is your relation with local administrations, and do you feel that local administrators are interested in what's going on? Which kind of sensibility do they have? And the other part, a little bit more technical, is about possible applications of your work in the field of renewable energy, green transition, and so on.
Maybe, I think the first question about local administration, in general, not very much, I would like to say. I don't have the only... it's interesting when I travel in different countries, the French embassies, they contact me. So more interest from this Nobel Prize for me is really going to 2 different countries, Sweden and France. And it's very nice. It's really double Nobel Prize for me. But so the French embassy is almost always contacting me. And then they ask me to go into French school of the different countries. And this will happen, I'm going to Rome, I'm going to Milan and then Rome. And in Rome, I will be actually, I will have lunch with the French ambassador. So the French politics are interested. Not so much the Swedish politician, I don't know. But this is, different culture, which probably means that science in France is very important. Now, the second question is, the green energy. I think it's too soon. And this is what I mentioned in the end. If we start to look at the dynamics, electron dynamics at the beginning of chemical processes, maybe this could have application. If we can do, synthetic, if we can help to make synthetic photosynthesis, something like that, this is obviously very, very important for our environment. But it's really too soon. I hope so, but we will see.
Let's hope so. Thank you very much. Is there any question? Yes, I see a few of them.
Hi, I apologize in advance because it's kind of a personal question. But I was thinking that now you got this huge result, which is a success of a lifetime, and everything is great, and everyone is happy. And on a much smaller scale, as students, physics students, experience similar smaller successes in our life, like passing an exam, or even just getting out of a lecture where we feel we understood everything, which is kind of rare sometimes. But in many cases, things don't go this way.
Yeah.
In many cases, we fail the exam multiple times, or we get out of a lecture with a deep feeling that we didn't get a single word, or it takes us much more years to get our degrees. And this takes a toll. It takes a toll on our time, on our self-esteem, and on our health too. So the question I wanted to ask you is, what if you failed? So what would you have done? How would you have felt?
So what did I fail? I think the career of actually both professional and private life, this is like this. This is never like this or like this. It's really like this. And I have really experienced that a lot in my life. So I think my recommendation is don't give up. Yeah. And enjoy when it's going well. And when you have this big or small happy moments, like, oh, suddenly you understand something. I think this was very nicely described, or you pass an exam. Just make sure you enjoy these moments, and remember then when some other times it's more difficult. But I have, it's not that I've been succeeding all the time and lucky all the time. Of course, I have had ups and downs like everyone. Yeah.
Thank you. Are there any other questions? Yes.
Hi, everybody. Professor Anne, I would like to ask you maybe something in trend about AI. Do you think maybe AI can join a little the fundamental research and the applications? Do you think you will be all of us able to maybe chart the path to join this kind of research with the final application? Is it useful or is also far away?
I am not expert about AI, so I think this is something, as a Nobel Prize winner, you are exposed to. People ask you to give your opinion about everything. There is even a name for that. It's called Nobelitis. It's the name of a strange sickness, which only Nobel Prize winners can have. So my answer is I don't know. Of course, AI is useful in small things that we are doing in a lab. We can retrieve something easier with, but I cannot give you a general answer.
Okay. I have two more questions, maybe more centennials oriented, let's say. The first one is, do you use in your lab, or do you use ChatGPT, or also do you watch some YouTubers, some advice about what to see in YouTube, or something you follow, even a newspaper, or something on internet you like to check from time to time that maybe you advise to us to continue to be growing?
No, I don't use ChatGPT. But I am old generation, you know, so no.
Okay, thank you. Are there other questions? A couple of them in here.
So first of all, thank you very much for your very clear, deep and far-reaching talk. And so my question is the following. You show that you're able to reconstruct some electron trajectory quite precisely. So how do you cope with the fundamental quantum mechanical obstruction to the observability or even the existence of the trajectories of particles?
Yeah, this is a very good question. We can do, it's a model, what I presented. And of course, to describe the process, you need to do quantum mechanics. You need to solve this Schrödinger equation. And actually, this is the third theoretical effort that I mentioned. It's a quantum formulation, which includes these trajectories. It's like Feynman path integrals, very much like that. But this simple picture where you calculate this trajectory solving Newton equation include a lot of physics of the phenomenon. Yeah. But of course, you need to do quantum mechanics. Yeah.
Thank you. The other questions?
Salve, io mi scuso per il fatto di rivolgerle il quesito in italiano, ma la mia competenza linguistica non è eccellente e l'emozione la comprometterebbe ulteriormente. Lei è un eccellente modello di riferimento per i suoi studenti, per la sua tenacia, il suo interesse, la sua passione e la sua capacità comunicativa. Volevo chiederle cosa le insegnano i suoi studenti e qual è il contributo che loro hanno apportato nelle sue ricerche e nei suoi percorsi che l'hanno portata al Nobel.
Grazie. The question is, of course you are a model for your students and for the people you teach to, but what do young students teach to you and which role do they have in your creation of knowledge and looking forward?
This is a very interesting question. I can answer several ways. First, I enjoyed teaching very much because, well, this is a little bit related to the question of ups and downs. Sometimes research simply doesn't work. Nothing is working. And the laser is dead, or you do something and you consider and you think, oh, but this is fun, but what is the use of it? Is all my career going to give something back to the society? Well, I don't know. You see what I mean? You really, I'm spending money from the taxpayers, but what is it good for? You have these doubts, and very often. When you teach, you have direct feedback from the students. If you see their eyes, oh, I understood this, then it's a direct feedback that what you do is actually useful. So this is why I like this balance between research and teaching, is because teaching is you do something for society and you see the impact direct. The research, maybe it will never have some impact, or maybe it will have some impact in 40 years or 100 years. You don't know. So, and now what I say applies also to the interaction I have with PhD students, because there it's a bit different. This is research, but you educate someone during 4 years in Sweden. You try to teach this person to solve problems, to have his or her own, way of thinking, to know how to write things down. So this is also very rewarding. And you help the society through this interaction with people. So for me, it's really very important. Yeah. I don't know if I answered everything you said, but yes. Yeah.
Yes, you did. Thank you very much. And I think we have time for a couple more questions.
Hello.
One is there.
Hello. In your very interesting talk, you've talked about also the applications to imaging techniques of the attosecond pulses. And I would like to ask, what would be the advantages of a well-developed imaging technique over well-established methods such as electron microscopy or atomic force microscopy? And I would also like to ask the obvious, which is if we can lower the duration more.
Yeah. Regarding the first question, I think I think electron microscopy or atomic force microscopy, they give information mostly in 2Ds. Whereas this imaging application, there is also information in 3D. And in addition, it's very fast. So I think that is the reason why they really want to develop this new technique, as far as I understand. But of course, you have better resolution with electron microscopy in general. But the resolution that they get is good enough for their application, and they have, in addition, the depth information. The other question was about pulse duration. The next step after attosecond is called zeptoseconds, 10 to minus 21 seconds. This is tough. So what we can achieve at the moment, the shortest pulse is measured is 43 attosecond. So it's a question of bandwidth. You need many frequencies in order to have short pulse. So if you you can generate harmonics going up to kilo electron volt energy. So the huge bandwidth. So this bandwidth is enough to reach at something like 1 attosecond. However, the problem is to this phase locking, to make all of these harmonics be synchronized or close to synchronize all of them together. So this is maybe more a technological problem. It's not fundamental, it's technological, but this is what prevents to reach even shorter pulses, is to have this huge bandwidth we can get, but this phase locking is much more difficult to achieve. Now, the other thing is that in our community, now we know that we can produce these pulses down to 40 attosecond. We really want to use these pulses. We are more, okay, we develop application more than trying to reach new records. That's also a reason why there is a stop which is around 40 attosecond. Yeah.
Thank you. We have time for one more, if okay.
Or two.
Regarding the Nobel Prize winners, the list of Nobel Prize winners is kind of a big album of great discoveries, and I was thinking it really isn't, because there are massive delays in the acceptance of the contributions of scientists, and some of them will not be able to accept the Nobel Prize, since only living people can have this prize. And I think it becomes relevant to this extent. Nobel Prize winning is something that everyone follows, and at least in the world of science, and so it is the main source of information that gives feedback to society and scientific community in order to understand what is important and take a direction. But there is a modification that pollutes the results in this way, with delay and not full accountability of prizes. Do you think this is actually remarkable? What effects do you think it has? Do you think it is modifiable? How would you do it, and how it makes you feel to have this, to receive this feedback after all these years?
Yeah, the reason for the delay, as you say, is that this is actually in Nobel's testament. This has to be a discovery or invention in physics, which is useful for mankind, which is a benefit for mankind. And this takes a lot of time in some cases. In some cases, like gravitational waves, then it's obviously something important for humanity to know that there are gravitational waves, so the prize come quite quickly afterwards, like 2 or 3 years. But in some other case, like our field, it took many years to grow and to realize, yes, there can be application. And to be frank, I don't think we really I mean, it's not a lot of benefit for mankind yet. It will come. But at least it's the benefit of mankind can be understood in two different ways. The benefit for everyday life, and this example, COVID vaccine, but benefit for everyday life, and also that the humanity has really reached a new knowledge, which is very fundamental and very important to understand better the nature and the world around us. But in many areas, it takes time, and this is the reason for the delay. Also, the procedure, I think one of the reasons for which the Nobel Prize is so prestigious is that the Nobel Committee over the years have managed to award the prize to good people you find in textbooks, for example, and not to make too many mistakes. And this is also a reason for this delay. It's not trying to go away from hypes. Yeah. But I mean, there are mistakes still, but yeah.
Thank you very much. I think this perspective on how science works is a wonderful conclusion for our chat. We have run out of time, unfortunately. Just before the final greetings, one technical information. Alla fine della conferenza gli studenti di CISF si possono radunare qui sotto al palco, così facciamo una foto istituzionale di rito, mentre il comitato organizzatore può salire qui sul palco. So we are at the very end of this event. Thank you very much, Professor Lullier, for being here in Turin.
Thank you.